In this lesson, we explore how LTI systems are described by differential and difference equations. For a continuous time LTI system, the input-output relationship takes the general form: the sum of a sub k times the kth derivative of y equals the sum of b sub k times the kth derivative of x. The left side involves the output y of t and its derivatives, while the right side involves the input x of t and its derivatives. Our goal is to find y given x and the initial conditions. To solve the differential equation, we split the solution into two parts: y equals yh plus yp. The homogeneous solution yh satisfies the equation with the input set to 0. We try yh equals e to the rt, substitute into the left side, and extract the characteristic equation: an times r to the n plus ... plus a1 times r plus a0 equals 0. Each root rk gives a term ck times e to the rkt. For a second-order system with two distinct roots r1 and r2, the homogeneous solution is c1 times e to the r1t plus c2 times e to the r2t, with constants determined by initial conditions. The particular solution yp matches the form of the forcing input. We choose a trial function from this table. If x is a constant k, try yp equals c. If x is linear in t, try c1t plus c2. If x is exponential, e to the negative at, try capital C times e to the negative at, but only when negative a is not already a root of the characteristic equation. For sinusoidal inputs of cosine omega t, try c1 cosine omega t plus c2 sine omega t. Substitute yp into the full equation, collect terms, and solve for the unknown constants. Let's walk through a complete example. The differential equation is the second derivative of y plus 5 times the first derivative of y plus 6y equals 2x plus the first derivative of x. The input is x of t equals e to the negative t. First, the characteristic equation, r squared plus 5r plus 6 equals 0. This factors as r plus 2 times r plus 3, giving roots r1 equals negative 2 and r2 equals negative 3. The homogeneous solution is c1 times e to the negative 2t plus c2 times e to the negative 3t. For the particular solution, since x equals e to the negative t and negative 1 is not a root, we try yp equals capital C times e to the negative t. Substituting, c minus 5c plus 6c equals 2 minus 1, so 2c equals 1 and c equals 1/2. The full solution is y of t equals c1 e to the negative 2t plus c2 e to the negative 3t plus 1/2 e to the negative t. The constants c1 and c2 are determined by initial conditions. Discrete-time LTI systems are described by difference equations. The general form is sum from k equals 0 to n of a sub k times y of n minus k equals sum from k equals 0 to m of b sub k times x of n minus k. Dividing by a 0 and isolating y of n gives a recursive formula. Y of n equals the weighted sum of current and past inputs minus the weighted sum of past outputs. This lets us compute each new output sample step by step, given the input sequence and initial conditions. This is exactly how digital filters work in practice. Let's compute the output for the system. Y of n plus 1 quarter, y of n minus 1 equals x of n plus 2 times x of n minus 2. The input is x of n equals the unit step u of n with 0 initial conditions. Rearranging, y of n equals x of n plus 2 times x of n minus 2 minus 1 quarter times y of n minus 1. At n equals 0, y0 equals x0 plus 2 times x of negative 2 minus 1/4 times y of negative 1. That gives 1 plus 0 minus 0 equals 1. At n equals 1, y1 equals 1 plus 0 minus 1/4 times 1 equals 3/4. At n equals 2, y2 equals 1 plus 2 times 1 minus 1/4 times 3/4. That's 3 minus 3 over 16, giving 45 over 16. Each step uses the current input, past inputs, and past outputs. Today we saw that continuous time LTI systems are modeled by differential equations and solved in two stages: the homogeneous solution from the characteristic equation and the particular solution matched to the input form. The full solution is y equals yh plus yp, with constants set by initial conditions. For discrete time systems, difference equations lead to recursive computation. Each output sample depends on past outputs and current and past inputs. Both approaches capture the same fundamental idea. The structure of the equation determines how the system responds to any input. In the next lesson, we'll connect this to the impulse response and step response.